Let me introduce the first speaker and chair of this meeting, Professor Chen from Zhejiang University. And Professor Chen is a professor at College of Control Science and Engineering, and he's wearing a number of hats. He's a director of the Institute of Industrial Intelligence and Systems Engineering. He's a deputy director of National Center of International Research on Quality Targeted Process Optimization and Control, and the director of Zhejiang University Amino Joint Lab on Smart Manufacturing. He's going to discuss with us some of the projects that he's doing there. So without any further ado, let's welcome Professor Chen.
Thank you, Mariana. Thanks for the nice introduction, and thank you all for sitting here. And it's so nice. Today I'm going to talk about the dynamic modeling of complex process using hybrid model. We know that many applications are modeling. So basically, they can be divided into two types. First principle models and data-driven one. The first principle modeling technique makes us the chemical engineering different from the other discipline. And we always do the first principle model at first. And it has shown successful applications, especially in the process design. And however, when we apply it for an online prediction, sometimes we feel it's not so accurate. So we also talk about data-driven model. As a control guy, we all know that, in my opinion, that system identification is the first generation of data-driven method. Though the computer science guy may know little about it. Nowadays, we talk about AI, talk about machine learning, but we control guys know that system identification work for a lot of successful applications. That's because we put excitation into the process. So this helps us to capture the dynamic feature. Especially for the dynamic modeling we are talking here. However, even the system identification works well for many cases, we still face this problem. We know the limitation behind it. Otherwise, we won't leave the room for the new generation methods. And often we face the situation that neither the first principle model nor the data-driven method work very well for a specific application. Therefore, we further propose the hybrid method. That's the topic we are going to talk today. Even for hybrid approach method, even for hybrid modeling technique, a lot of applications. A lot of applications means there's no universal way, right? So I'm not that ambitious to give you a universal solution here. I just want to share what we have done on industry and try to present some general feature behind it. Okay, so this is the process we are under studying, and you can see it's a quite complex one with 7 reactors. It has a counterflow reactor network. One raw material flow from the left to right, the other from right to left. And it's a nitration process, which means it has explosive risk. Okay, so the most important thing for this is to care about the safety. Okay, so the first task we share here is to develop a soft sensor for the quality prediction at the exit of the fourth reactor. it's important to control the concentration here to make the whole process safe. Okay, so it's a typical software sensor development task. A lot of methods have been proposed on this topic, right? Yeah, and nowadays it seems that the data-driven dominates, at least in publications. Yeah. So what we are facing here is to deal with the time series problem. Yeah, we have inputs including temperature, pressure, and flow rates. We want to predict the concentrations. And what I would like to share here is that how we did by proposing a method to improve data-driven modeling by integrating the physical structure of the process into the model development. If you develop a first principle model, no problem, you already consider the connections, the unit operations behind it. But if you use a data-driven model, usually it's a black box. So what we thought, can we have more information from the structure of the process to make the black box a little bit knowledgeable? So we know that LSTM, yeah, it's a quite fashion new method for dynamic process model, which can capture the temporal feature of a process. They feature all the input information and the input into this LSTM structure. I don't have time to give details of LSTM, just know it's for the dynamic process with neural network. Basically, it's a kind of recurrent neural network. Okay, so here, what we are going to do is, if you look at, that's the process. If you shrink the reactor node, if you shrink the reactor into a reaction node, is it very similar to a neural network connection? Right? So what we proposed is to mimic the process, the real physical process connection, and develop a neural network connection quite similar to this real one, and hope they can mimic the behind the physical features. Okay, so the top layer shows the physical structure, and we have the input feature matrix by combining temperature, flow rate, pressure for each reactor. Then we shrink we input this feature matrix into what's called the virtual reactor node. Okay. Then we combine them together by using a bio-STM, which is a STM but connected bidirectionally to mimic the real process connection here. Then we output the spatial feature matrix for each reactor and input it as a matrix FT here. Then we further expand the matrix FT at a different time step and use a conventional LSTM to represent the temporal connection or the temporal feature, or to extract the temporal feature. So we further construct another LSTM. And the output of the previous result is stored in this matrix H. If you directly connect it with another fully connected layer and output for the quality prediction, it can work. But still, instead of doing that, we further combine with attention mechanism to reinforce the spatial and the temporal feature extraction simultaneously. Okay, so as a summary, this plot shows the whole structure of the neural network we developed. Basically, it consists of 3 parts. The spatial feature extraction by using a bio LSTM, and a temporal feature extraction by using conventional LSTM. Then we use attention mechanism to reinforce the simultaneous spatial temporal attention. Okay, so now you can see that's our original input, and here is the output, the eventual output. Okay, then let's have a look at the results. We have compared 5 neural networks. The conventional one, multi-layer perceptions, we know it's good sometimes for the static process, but for dynamic one, usually it won't work very well. Okay, and combine them with LSTM, we make it to keep the temporal feature, and further combined with bio-STM, we make it have spatial feature. And if we combine them together, we make it to keep both the spatial and the temporal feature together. And eventually we add the attention mechanism to further improve its performance. Okay, here shows the results. This is the static results with the static neural network. We can see the result is not very good. On the contrary, it's quite poor. And by incorporating the temporal feature extraction with LSTM, sorry, here, that's for the spatial one. Yeah, it's a little bit improved. If you combine it with LSTM to keep the temporal feature extraction, a little bit improved, because it can somehow know to predict for dynamic process. Okay, but if we keep both spatial and temporal feature extraction into it, that's a false result. We can see an obvious improvement in contrast to the other previous results. And if you further put the attention into it, we can get the best results. So that's the first case we share here. The key point is that we developed a hybrid technique by integrating our physical process connection knowledge into designing of neural network. Okay, I don't think it's universal, but the idea is quite general. Yeah, you may have different applications. Yeah, you may try to design your special neural network to make use of the connections, at least at the unit level. Okay, that's a first example. Okay, still this plot, still this unit, we have another task. We have another task to predict the temperatures of the reactor network, which means we need to predict each reactor temperature. You may ask why there's a transducer there, right? Yeah, the point is that the temperature is very important to keep safety of this equipment. So we have this scenario to predict the 5 minutes ahead temperature of the equipment, which means suppose the operator leave without any actions during the next 5 minutes. Can we predict what the temperature goes to? Okay, the company likes this very much because it relates to safety, to avoid of explosive risk. Okay, and also the good point for this task compared to the previous one, we have a lot of online measurement. We have sufficient data. Yeah, compared to the previous results, because we only have offline data for the concentration for every maybe 8 hours or a day. But for temperature, we can have the online measurement every second, every minute. So we have sufficient data. And also, the reason we do this, because this process changes the operating condition a lot. They have a lot of because of the demand or other reasons, they need to change the load. For example, here, they increase the load by about 15%. Yeah, here shows the flow rate of the raw material fade. And the other subplots shows how the temperature varies during this transition. So, and also for this process, they need to keep the temperature varying within 1 Celsius degree. That's why this temperature control is very important. Yeah. Okay, we did both the first principle model and the data-driven model separately at first. And neither of them work very well. Neither of them work very well. I will show the results later. Okay, let's first have a look at the data-driven method. Here you can see, here shows the example of the results. If you look at the results, you can see very good agreement between the prediction and the real measurement. Yeah, but wait a minute. If you zoom in, you can see what happens. You want a multi-step ahead prediction, but what you really get is only a lag. Which means the model you got is useless. So don't be blinded by the so-called mean square error and then other statistics. Yeah. When we do modeling work, this kind of error often happen in practice. Yeah. So for data-driven model, it's easy to be trapped into this kind of step lag problem. Yeah. So that's what we need to avoid. Okay. So as a control guide, for this case, we definitely first comes out to this idea, the OX model, right? It's an autoregressive thing. We have the past temperature. We want to predict the future temperature, right? That was developed decades ago. So we first tested this. If you look at the error, it's quite low. It's quite low. Yeah, and both for the training data and the test data almost the same level. Yeah, but if you look carefully, you can see it's a time lag, like here, 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 here. So this kind of model, maybe from the error is very small, but it's not what the company really want. Okay? If you use the current days, the new fashion method, like the sequence to sequence, this should be the most feasible one according to the idea. You want to know the sequence of this temperature variables. Still here, because you have a large neural network, you can fit anything you want. If you look at the training error, very, very small. Yeah. But if you check at the validation error, it's quite large, means overfitting there. Also, if you look at carefully, still the lag, the time lag problem, the time lag phenomenon occur here, which means this is also not the model you want. Okay, then we test the first principle model. We developed the heat balance, the kinetics behind it. Something interesting, like this is for reactor 1. you can see they can give the trend, very good trend of the temperature variation. But quantitatively, if you look at the error here, if you compare it with previous data-driven methods, the order of magnitude is several order higher. Yeah. So quantitatively, it's not so good. Yeah. And but the good point, we don't have the time lag problem. Yeah. And also, if you compare between the training data and the validation data, they are almost the same level. That's a good point for the first principle model, right? Yeah. So the hybrid technique comes out, works on the stage now. So we proposed to develop the first principle model by using our knowledge behind it. We describe it and make it as a state space one. Then we use Kalman filter. That's a control guy, always think about it. The idea is that we keep a first principle structure, but varying the parameters, or tuning the parameters by using Kalman filter. Okay, we call this UKF plus FP. Okay, here shows the results. We can see an obvious improvement for all the 7 reactors here. And we can conclude that the hybrid technique works here. But we still know the Kalman filter cannot work everywhere. There's still limitations behind it. So considering the limitations here, because here the state space model we use, it's only first order one. It cannot capture a long-term dynamic feature behind it. And therefore, we combine with the sequence to sequence afterwards. Okay, so the motivation to combine this sequence to sequence network again, because we want to explore more capability for dynamic feature extraction. Okay. Okay, so basically the sequence-to-sequence compensates for the unmodeled dynamics by the first principle model. We also employed encoder and decoder to solve the previous disadvantage behind the Kalman filter. Okay, here shows the results. That's the best we have now. Yeah. 7 reactors. We cannot see perfect, but at least our company collaborators are satisfied with this. Yeah, we use it online. We use it online for the prediction. And if you look at here, still we have better results for training data set than the validation data set. But anyway, they are almost at the same level. Yeah. If we put all the method results together on one plot, each plot is results for one reactor. You can see the final results has the best performance in all cases. Okay, the box plots can also reveal the advantage. The last column are the final results we used in online. And also you can see, compared to the other methods, the last one has almost the same level between validation and the training data sets. That's also, which means they have consistent performance. Okay. Okay, I'm almost time. Okay. At last, I would like to acknowledge Amino company Afterwards, in the industry session, our Armenian friends will talk more about our applications there. And also, I would like to thank the Zhejiang province for the funding. We also thank Armino for funding us to build a joint R&D center. And I would like to thank my PhD student Chen, mainly his work, and Ren Jie. And also last to thank Professor Zhu from Zhejiang University of Technology. She helped us to build the first principal model. And if you have interest on the details, please refer to the 2 publications recently published. Thank you all.
Okay, thank you so much.